And you need to get a ruler, and you're going to make 2 sections. So a section here on the top, trace the ruler, and then move down some, and a section here closer to the bottom. So your paper is going to look something like this. Ultimately, we're making this. So you got to have enough space for you to do this. Okay, so pause this whenever you need to so you can start the paper. And then we'll go on from there. Are you guys done yet? Are you ready?
No.
Get there!
I did a different one.
Okay, you're going to need one colored pencil that's dark. Yes, it needs to be a colored pencil, not a marker. Okay. So at the top, this is going to be a continuum of electrostatic forces. So continuum of electrostatic. Okay, electrostatic. Remember, electrostatic is just referring to positive and negative charges that attract each other. So I'm going to make this bigger. Continuum of electrostatic forces. Okay? And I'm going to label it, and I'm going to put, and again, I'm just kind of estimating where these things are. I'm going to take this same dark marker and about right in here, I'm going to put a line here. And on one side, these are all physical bonds. So no chemical bonds, just physical. And on the other side of this little line, it's going to be chemical bonds. Now, when I say physical bonds, what I'm talking about are attractions between molecules. IMFs, intermolecular forces. And then what I'm going to do is I'm going to put on this side, I'm going to write weaker. These are the weakest, the weaker ones. And then on the other side, I'm going to write stronger. So weaker's over here, and stronger gets over here. Okay. Now I'm going to pick my colored pencil that I chose.
Stronger on the other side, like on the left side?
Stronger over here.
Like, oh.
Weaker over here. I'm going to take my colored pencil that I chose, and I'm going to color this band in, and it's going to be light on one end and dark on the other. Light where it says weaker, dark where it says darker. So where it says stronger there. So the continuum is the fact that the bonds, there's not just this sharp delineation of here's a chemical bond, here's a physical bond, although we can kind of arbitrarily state that. But what it does is, over here, you have attractions between electrons in the positive nucleus, right? And they just get steadily stronger as you go across until it comes to a point where it's such a strong thing that a new substance is created because they're chemically combined together. So you're going to start on the weaker side, and this is where you're going to color in very, very lightly. And then as you go across, the color is going to get more saturated as you go across. So that when you get over here to the chemical bonds, this is where you're going to be darkest.
Can you just do a little bit of the whole?
You're doing the whole line. So if you look at this that I have already made, it starts lighter over here, and it just gets steadily darker as you go across, until the darkest is over here where you have the strongest bond. So I can't pause this video because the video pauses but the sound doesn't, which keeps the video going, which is weird. So let's just color it together, children. And then if you color too dark in one area, you know, you can always go over it or with an eraser. It'll take some of it off. And you should be able to kind of go over it with your finger. You guys who are artists know how to do this. I'm not too good at this. Now, the chemical bonds are significantly stronger than any of the physical bonds, right? Physical bonds, you can usually break those with your finger. You remember when we put the paper clip, set it on top of the water, the surface tension? We had those, that's just basic hydrogen bonding. When you do that, you can they're just physical bonds. You can physically bump them apart. So you could get that paper clip to drop down and break that hydrogen bonding easily. It didn't require any chemical reaction to get it to break. So when we look at this now, and I'm going to have another colored pencil in the same family as the one that I started with up here. So I've got kind of a blue-green, so I'm going to get a green associated with that. Again, a fairly dark one so that you can get really dark, and then you can get also a little bit lighter, get it really light. Okay, so I'm going to start way over here on the weaker side. And again, you need a dark pen so this stuff will show up. So we're going to start way over here, and we're going to say this is where the IMFs would be. And remember IMF, do you guys remember what IMF stands for?
Intermolecular force.
Okay, I'm going to write that below there just in case. Intermolecular forces. Notice it's molecular, not ionic. So these are between molecules. This is what we're talking about, between molecules. So ionic compounds don't have intermolecular forces. And the reason for that is because when you have an ionic compound, if one ionic compound is attracted to the other, they're all hooked up in one crystal. So intermolecular forces. An example of this, and really the one that you most need to be aware of, and that are the weakest, over here would be the weaker ones. I might even say, I could change that to weakest if you want to make that makes you happy. Weakest. Here we have the London dispersion forces. LDFs. We don't care about that. London dispersion forces. Dispersion. And London dispersion forces, and you're going to need to write this down if you can't remember this. London dispersion forces are accidental polarities. So I'm going to write accidental poles. And I say accidental, it's just random. Maybe random would be better than accidental. So basically you have this molecule, and it's got electrons swarming around, right? So at some point, just randomly, more electrons are on one side of the molecule than on the other. So it has this momentary polarity that happens. Just random, just momentary polarity. It doesn't last, but it's something that you can actually have that has an impact. So London dispersion forces. And the bigger the molecule, the bigger the force, the more common this is going to happen. So bigger molecules have more London dispersion forces. So these are, you can pick whatever words you want to use. I put accidental poles, polar poles, negative, positive, random, you might put random, something along those lines, but they just randomly happen. And the bigger the molecule is, the more likely it is to happen, because if the bigger molecule, then yeah, it's much easier to get all the electrons more leaning towards one side of the molecule than the other. So this is the first of the intermolecular forces, the London dispersion forces. And they're the weakest ones. They're momentary, they don't last very long. But the bigger the molecule is, the more impact it has, and it actually has an impact on the boiling point. So if you have a compound and you say, well, this should be the boiling point compared to these other ones that are like it, if this one's a bigger molecule, the boiling point's actually going to be a little bit higher than what you predict, because they're going to be these random forces of attraction between molecules. And the whole thing with boiling, don't you want to separate the molecules into a gas form? Yeah, so if you have these intermediate, these little minor attractions, then it's going to just take a little bit more energy to get them to separate out. The next one of the IMFs, and these are all IMFs on this side, would be the permanent dipole-dipole. Yes, they call them dipole-dipole. Makes me crazy. Permanent dipole-dipole. This means the molecule is polar. It's always polar. Usually it means that there's an unshared pair of electrons somewhere in there, and it's not, it's more on one side than it is on the other, and so we have a permanent dipole setup. So you'll see it on the test, it'll say dipole-dipole. If it's an ion-dipole interaction, it means, hey, this molecule over here is polar, and it's attracted to this ion that's over here, because you put them both in the water in the solution. So maybe you put sugar and salt. Why you do that, I don't know. But maybe you put sugar and salt in the same thing. So now you've got those little Na ions and the Cl ions, and then you also have this polar sugar. And so they can be attracted to each other. So that's what, and the first time I ever saw that was in a question. You guys, was that in one of the questions? That ion dipole? Yeah, that's the first time I ever even saw that, and I thought, well, yeah, I know what it is, but I never would have said anything about it, because why? So apparently the AP says, yeah, you need to do this. So this is a dipole-dipole interaction. So you've got a polar molecule that's attracted to another polar molecule. Yeah. In many cases, they talk about these, it's the same compound, so you have all the molecules are the same, but they're obviously polar, and so they can be attracted to each other. The whole thing about putting two different chemicals in there, that's kind of new on the AP to say that, because that obviously means you've got two different chemicals. So in most cases, they usually talk about the same chemical. It's all the same molecule in there, other than water, which is always there. And then we have another IMF, which is the strongest of the IMFs. And again, these would be the hydrogen bonds.
Can you scoot it over, please?
Yep, sorry. The hydrogen bonds. These are hugely important. They're between hydrogen in one molecule and FO or N in another molecule. And the FO or N has to be bonded to a hydrogen. So between hydrogen now, when I say that, again, usually it's all the same chemical. So other than water, that's always going to be present in solution. And again, we're talking about solutions. You can talk about IMFs in a solid, but it's like really there's no need to, because obviously the solid particles are stuck to each other, right? Yeah. So really we talk about this in terms of solutions. Gases, if it's an ideal gas, which is what we want, then they're not going to have any IMFs at all. No intermolecular forces. There are no forces of attraction. So it's all about solutions. Something dissolved in water, or it's a pure liquid that's there. So we have IMFs here. All right, so let's go back. We've got the general basics going on here. Let's go back over here to the IMFs. These occur, the London dispersion forces, they occur between non-polar molecules. So if during this unit you're going to have to tell is this molecule polar or not. And so when we talk about London dispersion forces, these happen in non-polar molecules. So even when something is non-polar, you can still have these IMFs that occur. The bigger it is, the more likely you're going to have it. So these are going to occur in non-polar molecules. This momentary polarity occurs due to just a random movement of electrons. The bigger the molecule, so bigger molecules form LDFs more easily. And I'm going to call it LDF just because I don't want to write out London dispersion forces. I don't think they abbreviate that. They don't abbreviate it on the test. Just London dispersion forces. So that's my abbreviation, not the standard abbreviation. So the bigger molecules means you're going to have bigger LDFs or more LDFs. If these are the only intermolecular forces. Okay, so generally speaking, when we talk about London dispersion forces, we're talking about nonpolar molecules, right? However, a lot of times if it's a big molecule, it can have a piece of it that's polar and the other end's not, like soap. Soap has it's a big molecule. Soap has one end that's polar and the other end's not. And because it's like that, it can actually dissolve in both water and in oil. So it's a big Godzilla molecule, and one end has nothing to do with the other, just about. So if you have these big molecules, you can have pieces that are polar, and then when you get to these, they can also have LDFs. So you can have London dispersion forces, and you can be polar too. The bigger the molecule it is that can have that. So when we talk about these, if these are the only IMFs, so if the London dispersion forces are the only IMFs, then these substances are usually gases at room temperature. Physical noticeable impact. Because of these LDFs, the larger the molecule, the higher the melting point and the boiling point. Do you guys know MP melting point, BP boiling point? If you don't, you might want to write that down once. So sheerly because, and you know, a lot of times what they do, the big thing about what a lot of chemistry does is it tries to predict things. Like here we know all this information about these particular chemicals. Here's another chemical that's similar to that. What can we predict about that? And so they can predict, well, here's what the boiling point should be, here's what the melting point should be, and so on and so on. But when they find they have, as the molecules get bigger, the melting point and the boiling point increases simply because of these London dispersion forces, where they're just randomly attracted, and so it takes a little bit more energy to do that.
MP and BP?
Melting point and boiling point. much time do I have left till the bell?
10 minutes.
Okay, all right. So the next one we can do, and these things, and I'm going to write along here, if you'll turn your paper this way, these are temporary. All these London dispersion forces, these are temporary. They're momentary, temporary. They're not going to last. They aren't permanently there. And when I say that, they're not permanently in one spot, right? It's just randomly moving around like that. Now, the next one is when we have a dipole-dipole thing that's going on here. Now, I'm going to put this word first. We have neutral polar molecules. When I say neutral, the overall charge of the molecule is 0. When we create the molecule, don't we make the oxidation numbers equal 0? They add up to 0. It's a neutral molecule, but it's polar because the electrons aren't shared equally. Usually, these are liquids or gases at room temperature. And again, all of these are covalent, okay? All these things we're talking about right now are covalently compound. So if you want to write on here, you can write in here covalent if that makes you happy. We're talking about molecules, so it's definitely covalent in there. So when we talk about these dipole-dipole, these are attractions between polar molecules. Now, you can also have mixtures in two, and then you can also have, here's another one I'm going to throw in here with this, you can have a dipole-induced polar molecule, okay? So I'm going to bring this down a little bit and talk about this. So here I'm going to talk about mixtures. What happens when we have mixtures of stuff, mixtures of substances, okay? So a lot of times what they do is they'll talk about, okay, it's one compound that's in here, we're not worried about it, but what happens when you have mixtures of stuff? When you have mixtures of substances, what you can have is a dipole-induced. Do you guys know that word, induced?
Like put into.
It causes it to be polar. So you have a polar molecule and you bump it up against a non-polar molecule, and because the polar molecule has this side is positive, it's going to pull some of the electrons over in the non-polar molecule, and it's going to make that non-polar molecule have a polarity. Yeah? It's like putting something that's attractive up to one, or if you have some on the negative side, it's going to push the negative electrons away from it. So we call it dipole-induced. This is a polar molecule. Polar molecule causes a non-polar molecule to be slightly polar. So dipole-induced, again, that's one of those that I wouldn't have taught, but it popped up on the test, so it's like, there it is. And then the other one is the ion dipole. And this is an attraction between an ionic compound and a covalent compound. An attraction between ionic and polar covalent. And this is permanent, with the exception of this one. when you have a dipole induced, the one that it induces the polarity on, that's not a permanent one. So the mixture is a little bit iffy. But the ones that, hey, this is a polar molecule, that's a permanent thing. It's going to stay polar molecule. And then the last one is the most important. This is why we have life on the planet here.
Oxygen.
Water.
Water.
Water is a big deal here. So the positive end of one molecule is attracted to a very electronegative atom in another molecule. So this is the positive hydrogen
Do you need to put like do you need to separate it?
like from no, you don't need to. You can if it makes you happy. Be consistent.
Yeah.
Yep. So the positive end, hydrogen, is attracted to the negative end, to a very electronegative. Hang on, I got to write this down right. Hang on, don't write that. Where's my little thing here?
Oh, this.
Yes.
Sorry. I was like, what's she talking about?
Okay, so the positive end of one molecule, hydrogen, is attracted to a very electronegative atom. And that is FON. Okay, let me explain that because it's difficult to just put it in that one. One molecule, and think of these as the same types, same chemical, all same molecules all the way through. So hydrogen has to be bonded to an FO or N, and then that hydrogen is attracted to the other molecule just like it, but it's attracted to the FO or N. So again, think water is your best example. There's the O right there. So oxygen is hugely electronegative. Here's the negative end up here, the positive end down here. And so when you get these water molecules together, then the negative end is attracted to the positive end, yes? And you can say that the positive end here is attracted to the negative end. And it's always going to be, and they usually indicate it, and I've put these two close together to show on the board. They usually indicate it with, okay, here's the oxygen. And right here, there'll be this little dashed line. And that's a hydrogen bond. Yeah. So if they do this here, then there will be a little dashed line. So that's not a true chemical bond. Again, we can bump it with our finger and break it, but that's indicative of a hydrogen bond. So when you see this, I'm going to draw this right here. Then you have the oxygen is the negative end, the hydrogen is the positive end, and then when you have this other water molecule that's attracted to it, again, there'll be this little dashed line right here, and that'll be indicative again. It shows that that's a hydrogen bond here. So carbon bonded to, okay, so I'm going to put something else down here. This is not a hydrogen bond, but I'm going to put this as an also. If carbon is bonded to a fluorine, carbon bonded to oxygen, and carbon bonded to nitrogen, these are slightly polar. That just kind of fits on my paper down here. Okay, so the hydrogen bond is the strongest. If you look up here, weakest over here, and it gets stronger as you go by. Of the IMFs, the hydrogen bond is the strongest. Okay, you need to know that of the IMFs, the hydrogen bond is the strongest. And so this is also permanent. And instead of putting dots, I'm going to take this little squiggly line right here and continue it on down, because from this point on, it's no longer just an intermolecular force of attraction. Now we come to the point where These are so attracted to each other that they chemically bond. So they're lightly attracted to each other here, and they get stronger and more strongly attracted to each other, and more attracted to each other, and more attracted to each other, until there comes a point where it's like, holy crap, they are so attracted to each other, they chemically bond and swap electrons, or share electrons.
Can you scroll it down?
Yeah.
There.
Okay?